All right, so I'm getting better with the portable mic. We're almost done with chapter 2. And one of the things to remember about chapter 2 is that each of these sections is pretty much a new idea. And so it's a lot of stuff to sort of take in at one time. We're going to talk today about cylindrical polar coordinates. And so I'm just going to remind you of what we've done so far. So we've defined an xy coordinate. I'm just going to leave it as two-dimensional for now on because there's not much point to talking about z. So r is equal to xi, yj. And remember that with an nt coordinate, you're not really defining position. So you just want to know the magnitude, the length of or the distance you travel along a path, and we just call that s. When it comes to velocity, this is a little bit nicer as a coordinate system in the sense that all I need to know is the magnitude of the speed, and it's acting in the direction of the tangential. So that kind of makes physical sense. In a excuse me, xy coordinates, vxi, vyj, or dr dt. Finally, acceleration. And with acceleration, you still have ax, ay, or in the nt coordinate system, it's acceleration tangential, acceleration normal. So one of the things that as you're looking for things to put in a crib sheet, this is the sort of information you'd want in there. Acceleration tangential, we get that directly from the first part of the derivative of dv dt, and it gets v dot. This term, v squared over rho, comes from the derivative on the unit vector. So remember, the second term was v et vector dot, and after you were all done, you kind of had a v over rho that appeared. And so you multiply that with the current v, and you get v squared over rho. So that's our normal acceleration. And one of the things that you kind of guess at this point is that the complexity of the coordinate systems goes up a bit. So x, y, I think everybody really has a good handle on those. They understand what they are. Nt is a little bit odd, but we don't have to worry about direction or position. And so the terms that you got to remember are a little bit less complex. But the last coordinate system, and I'll sort of talk about it first as a definition and then go back and look at the unit vectors just briefly again, is a r theta, or polar coordinate system. So in my figure eventually, there we go. I can define an xy. So I can put a coordinate system down. There's the coordinate xy, but I can also define a coordinate system that is, again, coincident with the same origin. So its origin is going to be O. I better just give that a definition here. And I can look at a particle traveling along this curved path. So you see this curved path in blue, and as you sort of go on, you see it at two different times. You'll notice that I can define the distance. I'm going to switch pens. Yeah. It may be better as. Okay. So to define position, it's a lot like the position was defined with, or the velocity was defined in the NT system, in that one term describes everything there. So to describe this point right here at an angle theta, it's R1, and here it's R2. So the second position would be R2. You can see that it's defined with respect to the horizontal for theta. We've got a coordinate that sort of rotates around like this. That's theta 1. To get to theta 2, you keep going and you have a little bit more. Then I take its derivative. And its derivative is v equals r dot er plus r er dot. And this is where things get a lot more complex. I've got to worry about the unit vector now, and I can expect from my experience in the NT coordinate that that term is going to add extra things to this. And if I go through all of this without the derivation this time, I'll find that E sub r dot is actually in the direction of E sub theta, which is the normal component. And if you look at each of these particles, I have E sub r pointing outwards from the origin, and E sub theta that is going to be counterclockwise. And counterclockwise using the right-hand rule. So right-hand rule, put your wrist down at the origin, line your hand up with the x-axis, and then wrap it around. Positive rotation is in the counterclockwise direction. The world is designed for right-handed folks. So we have v equals r dot. This one's important. This one's important. And you can see right away I'm going to face another problem. And that next problem is that I will have to do the chain rule again to get acceleration. And when I do the acceleration, I'm going to end up with E theta dot and ER dot. So I already know what ER dot is. I just calculated it. But acceleration is equal to V dot, which equals to R double dot E sub R plus R dot E sub R dot plus R theta dot, R dot theta dot E theta plus R theta double dot E theta plus R theta dot E theta dot. Okay, so that's a big mess. And you can see that in my personal case, I really can't remember all of this, and I make sure that I write it down so that I have it somewhere later. But I end up with acceleration, which is acceleration r E sub r plus a theta E sub theta, in which case acceleration of r in the radial direction is r double dot minus r theta dot squared. Acceleration theta is equal to r theta double dot plus twice r dot theta dot. And I really need these forms. A very common error, if you do not put this, or make sure to sort of keep this referenced and sort of squared away, is to assume either the acceleration r is r double dot or acceleration theta is theta double dot. First of all, when dealing with thetas, they're always in rads per second, rads per second for angular velocity, theta dot, and for theta double dot, rads per second squared. I tend to write all of my units on every term. So even if I have a rad, which will disappear when I do a multiplication with r, I will still end up keeping it in my calculation. But these are the acceleration radial and the acceleration theta.
Sorry, so for a theta, is it r theta 2 dots plus 2r squared theta?
Nope, 2r dot theta dot. Let me see if I can make that look better. Ooh. Okay. The other thing you should always do when you're doing these types of things, r dot, I know right away is going to have meters per second. So it's a good velocity term. So that makes sense. R theta dot right here is going to have units of meters times rads per second. That will come out when I multiply them together as meters per second. So I know that that's correct too. So as I'm calculating things, I have to make sure I write all of these terms out. Down here, I have meters per second squared minus meters rads per second squared. And so both of those are meters per second squared. If I go down one more, I have meters rads per second squared. And I actually don't want to put the operation in here. I'm just going to do this. And I'm going to, meters per second, rads per second. So in all of these cases, I can check the units, and I should check the units to make sure that what I'm going to get out of this is an acceleration. So meters per second squared, meters per second squared. Both of those make sense. They sort of follow up. Okay.
I have a question.
Sure.
Is the time rate of change of E sub theta 0?
No. No, not necessarily, except in very specific cases. Oh, no, E theta dot, no, unless it's straight line motion. So I have all of those terms, and I always have to worry about them, but let's kind of go into that question a little bit. So ER is equal to, looking at my coordinate system and rewriting it in terms of xi, or ij, is just going to be cos theta I plus sine theta j. Taking the time derivative of that, will equal theta dot multiplied by minus sine of theta plus cos of theta j, and there you go. So ER dot is perpendicular again to ER. And again, this is kind of important. If you don't have to rederive these relationships. You just have to know what they are, and this helps you understand where they're coming from. But it ends up that ER dot is equal to theta dot E sub theta. And that's where I'm getting my terms for my velocity. Now, you could see up above somewhere that I also have an E theta dot. And that's equal to minus sine of theta. Minus sine of theta I plus cos of theta j E theta dot is equal to theta dot minus cos theta I minus sine theta j. So again, I have something that's acting perpendicularly. And E theta dot is equal to minus theta dot E sub r. That's good. That's useful. So as I'm going through all of this stuff, as you're sort of dealing with this, this is just to get you to understand both of these are necessary for these conditions right here, here, and here to occur. So we've been talking a lot about xy coordinates, and to be honest, we spend a great deal of time looking at xy coordinates. But one of the things that's useful is to recognize some of the differences if you have an NT system versus an R theta system. So let's imagine I have a particle that's traveling along that green circular path. So the blue particle can either go counterclockwise at the top or clockwise at the bottom. So it's going either, well, counterclockwise or clockwise. If I were to look at that particle, I can define E sub r, and E sub r is always outward. It always goes from the origin out to the particle or point of interest. E sub n points in towards the center of curvature. And the center of curvature is the origin, in this case, with a circular path. So E sub n and E sub r are in the opposite sense. E sub theta is always counterclockwise. So if you look at the upper top, or the top particle, it's going in the counterclockwise direction, or sorry, is it going counter? Yeah, it's going counterclockwise, and it's rotating in that sense. E sub t is going to depend, no, E sub t should be going this way. There. E sub t is also going counterclockwise because it's in the direction of motion. That's what you get for copying arrows. If I copy, or if I don't copy it, E sub theta r, oh no, that's okay. So E sub r in this case is wrong. Let's just scratch all of that out. So E sub r is in this direction. E sub theta, or sorry, E sub n is in this direction. E sub t is in the direction of motion, and E sub theta continues to be counterclockwise. E sub theta is fixed. It always has to go and follow the right-hand rule. E sub r has to point outwards. E sub n always points inward. Go ahead.
So I'm just a bit confused about the graph that was just above this. E sub r, E sub theta, why is it not pointing this way and it's pointing this way?
E sub r is point. I just chose a direction. So E sub r is pointing in that direction because that's where it's going. If I were looking at a point, or sorry, I would define everything with respect to theta. Theta is going to be normal to that direction. So if I were to look at it, for example, at this point, I would write it like this. I've just rotated it down here, down to the bottom, so that I can look at it and put down the 2 points. So I want a relationship between ER and E theta.
Wait, no, I'm a bit confused about the right-hand rule. If we use the right-hand rule, shouldn't E theta be going this way?
Oh, okay, so I might have, I just chose one direction for motion. So motion is going to sort of determine E sub theta. Yeah. But E sub theta here would, probably should have put it the other way around. Yes, you're right, I should have put it the other way around. Any other questions on that? I'll have to take another look at this. Ooh. So one of the things that often comes up is essentially looking at motion that is, okay, I don't want that there, that combines some of these features. So here I have a hydraulic actuator, and all it is that black portion that's going to move vertically upwards. It's a distance of 2.4 meters away from the origin, and I have an xy coordinate. And coincidentally, I also have an r theta. The r is the silver slotted bar that's shown there. The hydraulic actuator moves the pin P upwards, so P is right there. And it moves upwards with a velocity of 3j meters per second. Determine the velocity of the pin in terms of polar coordinates and the angular velocity of the slotted bar when theta equals 32 degrees. Okay, so I have E sub r, E sub theta, so it's moving up, it's rotating in the clockwise direction. I have y dot, which is given in the problem, and that's that 3 meters per second. So I know that r is equal to 2.4 I plus yj in terms of meters. I know angle is 32 degrees. I know r is also equal to RER. And I didn't calculate. I know that r dot is equal to y dot sine of theta. And I know that because in this particular case, it's a nice triangle. So the triangle is always straight. It's a right triangle. It's never going to change. Right there. How did I?
Where did the 2.4 come from?
2.4 came from this. So I have r dot. I have r theta dot, which is equal to y dot cos of theta. And I know, actually I don't need to do that. I don't have to leave it, I can leave it as that. So I know r dot, and the reason I'm writing it in this form is because I want this in velocity form, and so my velocity is r dot e sub r theta dot e sub theta. So I have both of those. I have directions. How did I do this? Yeah, maybe I should ask that question. How come? How did this work? One of the important things to remember is that we are throwing a whole bunch of coordinate systems at you, but the total velocity never changed. So the total velocity is y dot in the y direction, and now I need to describe it in terms of y dot and e sub theta, or v sub theta. So, oops, maybe this is not the way to do it. I have y dot right here. I have VR and v theta. So what I want to do is describe the components r and theta that make up y dot. So total velocity, so same thing as acceleration. We talked about this yesterday. Acceleration doesn't change in totality, but its component parts do change. Go ahead.
We just use like sine and cosine?
Yeah, in this case you can. You know the angles. All of this is a standard coordinate system, and you can describe it in those coordinates. And so continuing, you have r equal to x squared plus y squared square rooted. So again, one of the important points in all of this is we're not changing the physics of the system, we're just changing how we describe it. So now I have all of the terms that I need to do that, and I will find, after relatively little manipulation, y is equal to 1.5 meters, r is equal to 2.83 meters, r dot is equal to 1.59 meters per second, and theta dot will equal y dot cos theta divided by r, which equals 0.9 rads per second. So when I'm doing this, one, I'm taking that definition for VR, which is r dot, so I calculated that directly. But for the second term, I wanted theta dot. And because I wanted theta dot, I had to take y dot cos theta divided by r, this term right here, in order to extract it. All of the other terms everything is coming straight from the trigonometry, or geometry, excuse me. Any questions on that? Go ahead.
I'm kind of confused on how you got r dot equals y dot sine theta.
I'm sorry?
I'm kind of confused on how you got r dot is equal to y dot sine theta. Third from the bottom.
So I got y dot. Got theta there. So I'm taking this from the triangle. And that's why I spent, I drew that terrible drawing there. The drawing is really important as you're going through these because you're trying to describe everything in terms of these component parts. So the tricky bit here is recognizing that there's no x dot component, so it becomes a lot easier. But all I have to do is describe y dot in terms of r and theta components. So you can continue this. Now you're told what is the acceleration of the pin in angular coordinates? Okay. And what is the angular acceleration of the bar? Now this is a little bit funny because at the very beginning of this problem, you're told that you have a constant velocity v. So v is equal to 3j meters per second. Acceleration of the bar in xy coordinates is 0. Okay. So velocity of the piston, 3 meters per second j, so that's fine. Acceleration is equal to dv dt, which is equal to 0. So the acceleration of the bar is equal to 0. How can you have angular accelerations or acceleration of the pin? I can write theta dot is equal to 0.899 rads per second. And I can write y dot is equal to 3 meters per second. So what I know is I got theta dot, which is 0.899 rads per second, which I calculated just above. I wrote 0.9. I probably should just write 0.9 here. It ends up being 0.899 something, so it's in terms of numbers, it's fine. Meters per second. Theta double dot is there, and I don't know what it is. Y double dot I do know, and that's 0. Tan of theta hasn't changed. It's y over x. It's y over 2.4. And y is equal to x length times tan of theta. And x length is at 2.4 meters. I'm leaving it as a variable because it makes my life a little bit easier. Tunk, 2.4 meters, right there. And that's that length, the horizontal distance from the origin to point P. So I have that. No problem. Y dot is equal to x length theta dot secant squared theta. Y double dot equals secant squared theta times the quantity x length theta double dot plus twice x length theta dot squared tan of theta. You don't have to do this on an exam. I kind of anticipate that would be a question. However, on a homework assignment, that's kind of reasonable to do. And there are enough tools out there. If you look at Piazza, they're recommending, one of the instructors as well recommended integral calculator. Another one, or in my case, I really like Wolfram Alpha for things like this. If you're going to do this, you might as well use Wolfram Alpha. It's really extraordinarily powerful. Anyways, I have both of those. I know y double dot's equal to 0, but I don't know that theta double dot is equal to 0. So theta double dot ends up being equal to minus 1.01 rads per second squared. This is all geometry. It's very, kind of crazy geometry at various points, but it's all geometry. And the funny thing is that as you go from system to system, you will have terms that appear in terms of your components that will have value even though you might have 0 in another coordinate system. The important thing to realize is that if I set this to 0, I get rid of the secant squared term right at the beginning. I get x len theta double dot, 2x len copy, get rid of the x lens, subtract that off, so that's negative, but I have a theta dot squared and a tan theta. Those are both defined. So if you want to do this on your own, you should do it on your own. This is a relatively straightforward question. The only tough bits in terms of memorizing would be how to memorize all of the derivatives of tan and secants. But even that, in a homework assignment, is reasonable, just so you know.
Sorry, for secant squared theta,
Yeah.
and you said that disappears, right?
Sorry, so I can write another step in here. So this is equal to 0 equals to secant squared theta times the quantity x len theta double dot plus twice x len theta dot squared tan theta, because it's both sides are multiplied by, or that's multiplied by secant squared, divides out. I end up with minus x len theta double dot equals to twice x len theta dot squared tan theta. And clunk, clunk, those terms go away. Everything sort of works out. So out of this, you can get results that seem intuitively unlikely. So you have a 0 acceleration case that leads to an acceleration in another coordinate system. Go ahead.
I have a question if you scroll up. I have a question if you scroll up to the previous question. Yes, so for this one,
Yeah.
on the second half slide where you r theta dot equals y dot cos theta,
Yeah.
as well as line above, are you mixing two different coordinate systems?
I'm describing one coordinate system in terms of another. So I'm saying that this is equal to v sub r, and this is equal to v sub theta. And I just want to make sure I have this. So I have y dot, and I want to describe it in terms of v sub r and v sub theta. That's what I'm doing. So I'm building a triangle out of that, looking at the geometry. And often when you're faced with problems like this, that's the first step. So you don't go to the definitions, you use the definitions afterwards in order to extract out, for example, this term right here, or to go to this step right here. So these are, you know, I kind of like this example, not necessarily because of the integration, that wouldn't be reasonable on an exam, but in terms of sort of making you think about the geometry, that's great. Making you think a little bit about something that is intuitively unlikely but is actually physically realistic is the last part of the problem. Go ahead.
I'm just a bit confused how we got the last derivative of y double dot.
Oh, it's the derivative of this. And I'm not doing it in class. Okay, I will be honest, I did that one. I ran it through Wolfram Alpha. So I checked to make sure I got it right. All right, I'm always scared that this will happen. But that's exactly what you're doing. So you're just taking the derivative with respect to time of the first term and you get the second term. And so you can go step by step through this, much like I did for the first to the second to the third. And because you have so many terms, you end up adding them in. And the only term that's constant, x len, really doesn't play a role, so that's why you only have 2 terms in your chain rule. Okay? Okay. 249. Oh, go ahead.
At the start of the question, it said to write the velocity in terms of polar coordinates. What do we do it in terms of cylindrical coordinates?
Sorry, so polar and cylindrical I will use interchangeably. So that is going to be a problem for me because polar coordinates is more what I'm used to way back when. Okay. The only coordinate systems we have right now are rectilinear / Cartesian, which are the xy. We have the NT, which thank goodness there's only one name for them, NT, normal tangential, and R theta, or polar coordinates. Okay. I think this is similar to a quiz a few years back. And for those of you who don't know, there are modules, and you can thank Canvas for the craziness in terms of how we organize these things, but Canvas doesn't allow folders, so I can't reorganize things down, so it's a lot easier to see. But there is a module for Quiz 1 study, and so we put old quizzes in there. The only problem is, I think, 2021, because 2021 was a bit odd. That was a COVID year, and we were fully online. We haven't been before for Quiz 1 or after. But you'll see information about that. Okay. During a given time interval, a radar station tracking an airplane records the readings r as a function of r dot as a function of time 449.8 cos of theta t 11.78 sine of theta t kilometers per hour. And it also records r theta t as 11.78 cos theta t minus 449.8 sine theta t kilometers per hour. I've defined here E sub r and E sub theta with respect to the radar station, and you've got r going out there, you got theta right there. All right. Determine the speed of the plane, determine whether the plane is being tracked, or the tracked is ascending or descending. Is it rising or falling? And the corresponding climbing rate, i.e. the rate of change of the plane's altitude expressed in meters per second. And you can see right away that the trick here is recognizing, first of all, that you're dealing with kilometers an hour, and whatever answer you get is in kilometers an hour. And if you forget that, you won't remember it in the last part of the problem. So make sure you write your units. So we know V is equal to the magnitude of the two terms. So V is equal to VR squared plus V theta squared. And we're given from this V sub r and V sub theta. Both of these are given directly in the problem. So you can say how do I want to write this? Oh, no. I'm going to write it as this. So V squared is equal to 449, 449.8 cos squared theta, and I'm going to dump the t, 11.78 squared sine squared theta plus 449.8, 11.78 sine theta cos theta plus 11.78 squared cos squared theta plus 449.8 squared sine squared theta plus, or no, not plus, minus 449.8, 0.78 sine theta cos theta. So I know that that's equal to that. So this is a lecture example, and so one of the advantages I have in lectures, I get to choose the numbers, and of course I've chosen two numbers that cancel each other out. These two terms go away. Now, unsurprisingly, I've also done a little bit of a trick on the next bit where I recognize sine squared theta plus cos squared theta is equal to 1. So this term and this term and this term and this term can be rewritten as 449.8 squared times the quantity sine squared theta plus cos squared theta plus 11.78 squared times the quantity sine squared theta plus cos squared theta. Okay, so again, it's good to be the one in charge of choosing the numbers. So V is equal to 449.8 squared plus 11.78 squared, and all to the 1/2, and you end up with 450 kilometers per hour. So that's my first part of the problem. Now, y is equal to r sine theta. And I'm doing that by inspection. So I can see I have a theta here. I have r there. That's my y. So I'm just filling in the right triangle. So I got y equals r sine theta. Y dot equals r dot sine theta t plus r theta dot cos theta t. Y dot is equal to 78 sine squared theta plus cos squared theta plus 449.8 cos and sine minus 449.8 sine theta cos of theta. So that term goes away, and y dot is equal to 11.78 times sine squared theta plus cos squared theta, which will equal 11.78 kilometers an hour. And it's positive, so y dot, after I do all of the conversions and get this done on time, is 3.27 meters per second, and it's going upwards. So again, a nice problem for looking at axis conversion. Go ahead.
In the original equation that were given for 3r and theta,
Yep.
are we multiplying by t? The t in brackets, are we multiplying by?
The t in bracket is just saying that theta is a function of time. And I probably should not have written it that way because I hadn't written it that way up until now. So sorry, that's correct. It just, theta is a function of time, but it doesn't matter because I'm taking it at one instant. I am solving for it from there, and I'm doing the conversion. And this problem right here